Dropout is another very commonly used technique for regularization. It is the most effective and the most commonly used method of regularization. Dropout, applied to a layer, consists of randomly dropping out, basically setting it to zero, a number of output features of the layer during training. Let's say a given neural network layer normally would return a vector that consists of 0.2, 0.5, 1.3, 0.8, and 1.1 for a given input sample during training. After applying dropout, let's say we randomly drop the first value and let's say this value, then after applying dropout, this vector becomes 0, 0.5, 1.3, 1, 1.1, like this. Um, Here, visually, say we have a neural network that has, let's say, three neurons in the first layer and maybe two neurons in the second layer. And let's say we have these connections like these. So each neuron in the previous layer connect to the neuron in the last layer. So this is my previous layer and this is my next layer. Then what dropout simply means is randomly removing some of these connections during training, such that this node earlier it would receive an input from all three neurons, but then suddenly randomly it receives inputs only from two inputs, not all three. And this is done repeatedly randomly during the training process. When choosing a dropout layer or when choosing dropout, the important parameter for dropout is something known as the dropout rate. And it defines the fraction of the features that are zeroed out. It is usually set between 0.2 and 0.5. And here's an example of how dropout can be added to a model. Say you have a convolutional neural network, and let's say you have this first layer and the second layer. Let's say this is COM2D 16 neurons and COM2D 4 neurons. Then dropout can be added in the middle of these two convolutional neurons, say with a dropout rate of 0.25. Instead of specifying the dropout rate, we can also specify the keep rate, which basically is the opposite of dropout rate. So in this case, the keep rate would be 0.75. One of the issues with the dropout is that, say we have a neural layer, let's say with these 5 neurons, and let's say in the second layer we have so this is layer 1 and this is layer 2. Let's say we have neurons like these. And let's say there are connections between all of these nodes from previous node to all the nodes in the subsequent layer, right? And so on. And let's say we've applied dropout and then randomly remove maybe 20% of these connections, maybe 0.2, that is equivalent to 20% random removal. So what happens is during training, each node will only receive 20% of all of its input. So the summation of all the input weights and times is around 80% of what it actually would receive if it were to receive from all the inputs, right? However, when during prediction, we don't do dropout because we don't want to remove out important signals from the input data. So during prediction, if we keep all the weights and don't do any dropout, then this model, which was trained on only 80% of the signal, now suddenly receives 100% of the signals, and the model cannot make accurate predictions. So for this reason, we need to handle dropout during testing or during prediction separately. The first strategy to deal with dropout during prediction is to not drop any units during testing. Now, once again, when we actually do this, that is, we don't do any dropout, then the output of each neuron becomes higher than what they are normally used to see, right? So to mitigate that, this strategy is actually to scale down by a factor equal to the dropout rate. So if the dropout rate is, let's say, 0.5, then what we simply do is layer output equals layer output times 0.5. This way, Even when there is no dropout during testing, the model will continue to see what it used to see. So this is basically to balance for the fact that more units are active than at training time. At training time, maybe only 50% of the neurons are active, but during test time, I will have 100% of the neurons active. So the output of the neurons must be scaled down. The next strategy is to do something known as inverting the dropout. So here, instead of multiplying the layer output during testing separately, what we do is even during training, not during prediction, but during training, what we simply do is we drop out. Say, for example, we have input metrics like this. When let's say we do 50% dropout, such that you can see that 50% of the values become 0 randomly. For example, here, this one, all these are becoming 0. So now during training, what we simply do is the activation that comes out, we simply multiply by the factor that was used to drop. So if 50% of the numbers were dropped, then we simply multiply by 2 so that our actual activation is exactly what it would be without any dropout. So we basically do activation equals activation divide by the keep probability, which is basically multiplying by a scalar, to scale up during the training. And this way, the model always sees, in a way, effectively 100% of its input and never even understands that dropout actually happened. So with this setting, actually, all we need to do is during training handle dropout such that the activations are overall 100% of what they would be without dropout. But then the convenience of this is that during testing, we don't have to do anything. We can simply use the model without any dropout and without any scaling, and then everything else works out fine. It is surprising that such a simple technique of dropout works very well in deep learning. And many of us wonder why dropout works and it works so well. Here's what Hinton, who invented dropout, had to say. He was inspired by a fraud prevention mechanism used by banks, and that's what he was using as inspiration to come up with dropout. Here's what he had to say. I went to my bank. The tellers kept changing, and I asked one of them why. He said he didn't know, but they got moved around a lot. I figured it must be because it would require cooperation between employees to successfully defraud the bank. This made me realize that randomly removing a different subset of neurons on each example would prevent conspiracies and thus reduce overfitting. So the core idea is that introducing noise, this intentional noise in the output values of a layer, can break up something known as these happenstance patterns that aren't significant. So what this happenstance patterns are, maybe the model learned something weird, something very different, and if the model is doing very well, then such happenstance patterns, which are patterns formed by chance, are broken down by this process of dropout.